So now let's look at how to use symmetric encryption to encrypt a message. GPG comes with several different symmetric ciphers, and the cipher is just a cryptographic algorithm. Cas5 is the default. AES is the US government standards. If we would like to change the default, there's several ways to do that. At the command line, we can indicate the option --cipher--algo and then indicate the algorithm or cipher we would like to use. Or we can indicate as the same thing to make it a default in our configuration file. We want to make sure that we use a good passphrase, because if somebody can guess your passphrase, then they can unlock or decrypt a message. Because the text is simply encrypted with the algorithm along with a passphrase. So if you can guess the passphrase, somebody can decrypt the message. And let's see how we would use symmetric key encryption. So we have a fairly large file, big.1.txt. That's about 6 megabytes in size. And if we go into the man pages and search for symmetric, we scroll down a little bit, we'll see that the options to use right here are --symmetric or -C with a single dash. The explanation says this will encrypt with a symmetric cipher using the passphrase. The default symmetric cipher used is Cas5, but may be overridden with the --cipher--algo option. And so what we want to do, we can get out of this with Q. We'll type GPG-C and then the cipher algo. We want to use AES and then the name of the file, big.1.txt, and we hit enter. It asks us to enter a passphrase. We want to make it a good passphrase. And that took all less than a second. Now let's look at the files. Notice this is our plain text, and here's our ciphertext. Notice that this creates a binary file, .gpg, and that it's much smaller than the text. If you want to take a look at the file, see what it looks like. And this is the encrypted version of the file. We can now create an ARMOR ASCIIized version of this by using the --ARMOR option. Ask us for a passphrase. And now we have 3 versions, including one that has the extension .asc. It's a little larger than the GPG version. And then we can take a look at this with less. Notice it says this is a PGP message, and there's our ASCIIized armored version. Type Q to get out. Now let's decrypt both of those. And let's first change the name of this to something else, because it's going to end up overriding that file. And let's decrypt the GPG version first. So we type GPG, and just so you know, let's go back in, let's search for decrypt. And you see here the options to decrypt are --decrypt or just -D. And so we can type GPG-D and then the name of our GPG file. Notice that it indicates that it knows that it's an AES encrypted data. We provide the passphrase. Let's pretend we don't know the passphrase. Put something in. Encrypted one passphrase, however, it was a bad key. That means we need to know the passphrase in order to decrypt the file. Let's go in and put in our good passphrase. and notice that it scrolls across the screen. If we would like to output that to a file, we can redirect that output to big.1.txt or name it anything you want. Here we go. So if we take a look at that file, and there's the contents of the file. Now, so we should have two perfect copies of that file. If we want to make sure that they're the exact same copy, let's check it with an MD5 sum, then big.1.txt, and you see the hashes are exactly the same. And this was the original plain text file, and this was the file that was encrypted and decrypted. You see that it's exact same hash, so it means it's the exact same contents. So let's decrypt the ASCII version to show you that it works exactly the same. And we need to change this to ASC, and we're going to output that to big.2.txt. So now we're decrypting the ASCII version. We give it the passphrase. Notice that it too was encrypted with AES. Now we can run MD5 sum on all three, and you see all three hashes matched. So encrypting and decrypting doesn't change any of the contents of the file. So we've seen how symmetric encryption works. That uses a single key, and the key is your passphrase. Public and private key encryption is going to use your public key to encrypt a document, which is sent to somebody who then opens it with their private key. So to encrypt a document using public key encryption for a single recipient, we use the command line GPG -- recipient and then the user ID. We must tell it to encrypt it, and then we give it the name of the file. If we would like to encrypt for multiple recipients, we can do so by indicating multiple recipients on the command line. Notice the -- encrypt and the -e are the same. They're synonymous. And if we want to create an ASCII's armor version of that, of course, we just use the -- armor flag. So recall I downloaded a public key and imported this public key here. So what we're going to do is we're going to use this public key to encrypt a document, and then I will send that over to a system where my public key was created, and of course that will also contain my secret key, and then I will be able to decrypt this using my secret key. So we type GPG recipient, and it's going to be, in fact, let's just use our unique hex identifier 081888578 just to demonstrate that it works exactly the same whether you use the email identifier or the hex identifier. We want to encrypt that, and let's encrypt big.1.txt. Hit enter. Notice this warns us that there's no assurance this key belongs to the named user, and that's because that there were no signatures associated with the public key. Had there been others who had signed the public key, then the trust level for that user would be increased up to a point where you would not receive this message. So notice that it also tells us the information about the public key, including the fingerprint and the unique identifier, and it asks us, do we really want to use this public key? We type yes, and it asks us if we want to overwrite big.1.txt.gpg. So notice that when using the public-private key encryption, that we don't have to output the name of the file, we don't have to redirect the output to another file. This is automatically done by GPG. Yes, we can override it, that's fine. We type yes. And why didn't it ask us for our passphrase? Because the only time we would be asked for a passphrase if we were needing to use our private key to send, if we were using our private key to encrypt something to be sent to somebody else. If we used our private key, and so let's go back and let's look at the GPG file, and here it is. And so what we need to do now is we need to, let's secure copy this over to our Mint9 system, and here's the IP address if I can remember that. And so let's secure copy it over there. big.1.text.gpg and 23.132. And so it copied the file over to this other system. Let's flip back over here. And there's our file. And now I can use my private key to unlock that, to decrypt that file. So let's type GPG dash, we'll say decrypt this time, and the name of the file. Notice it says you need a passphrase to unlock this secret key. So notice that this provides for confidentiality because only I can open this with my secret key. I provide my secret key, passphrase, and that scrolls off the screen. If we wanted to output this to a file, we could do so like this. And it says, notice that it was encrypted with 2048-bit RSA key with this ID. Let's run an MD5 sum on it to make sure that it's the exact same text. And that was the previous MD5 sum we saw. Now let's look at creating a digital signature. Sometimes you might want to send somebody a document and you don't care whether the contents are confidential, but you want to make sure that the person who receives it knows that it comes from you, and also that it hasn't been changed, that is, the integrity is intact. And we can do so by signing a document with our private key. And we can either create something just called a regular signature, which creates a .gpg file, or we can use something called clear sign. And once again, this should be a double dash dash. And what the clear sign does is it makes a clear text signature. And then the content is in clear text and is readable without any special software. So let's take a look at how that works. And so let's make a clear sign, and you notice that that's one word, there's no dash in there, so that the PowerPoint is wrong. And then we can provide something else. .text is the name of the file. We hit enter. Notice that we're going to be using our private key to create the digital signature. So we need to provide our passphrase. And notice that we now have a file something else.text.asc. And if we look at the sizes of these files, notice that the .asc file is a slightly larger than the something else.txt file, and that's because that the signature is placed at the end of the document. And so if we take a look at this document and go to the bottom, that is our signature. Notice that this is not encrypted, but it does include a signature. So now let's copy this document back over to our Mint9 system, and we're going to see that there's going to be a problem, and I'll show you what that problem is. But these are good good examples when you do run into a problem, because it teaches you the problem solving strategies that you're likely to run into, and then ways to solve it. And so 68.23.132, it was copied over. Let's look at and there's our file. And now what we need to do is we need to verify that file. And the verification does two things. It makes sure that the file has not changed somehow in transit. That is, there's a hash that's calculated, and then that hash is signed with my private key. And by signing with a private key, it allows the recipient to determine the authenticity of the sender. And we verify something using --verify, and we hit enter. Public key was not found. So it checks to see if the key ID is contained in our public key ring, and it wasn't there. So I need to import this key ring, this public key, into the key ring before I can use the verification process. And so then we can output this to a file called philipcrager.asc, which is an ASCII armorize. It's going to create an ASCII armorized version of the public key for me. Let's take a look at that file. There it is. And now we can copy this over to the other system. Let's go back over here. And there's my public key. This is PGP public key block. And now we can import this key. Notice that it says it imported one RSA key. Now let's go back and let's verify this. And this time it ran. The signature was made on this date at this time with this RSA key. It's a good signature from me. This key is not certified with a trusted signature, however. So once again, if we have other people who have signed our key indicating a level of trust, is that at a certain point this key becomes more trusted. Notice the primary key fingerprint is this, which also allows us to check the fingerprint of the sender. Now let's get a little more complicated. Let's look at signing and encrypting. And so if we want to make sure that the authenticity of the sender is checked, as well as the integrity of the encrypted message, and we want to provide for confidentiality using encryption, we can use the command GPG. We can armorize it if we wish. We can send it to the recipient user ID, so we're going to use our public key to encrypt it. The -E stands for encrypt, and --sign. So let's encrypt and sign a file. Let's look at the MD5 list. It's a small file that contains a list of hashes. Let's encrypt and sign that. So GPG, we want to armor it, and the recipient will be Craig EP at DaytonaState.edu, and we want to encrypt that and sign it, and then give the file name MD5 list. So it's asking for a passphrase for our secret key, our private key. And notice the order in which this occurred. First, it's going to sign the message, and the reason is that we want to have the hash calculated of the raw file, not the encrypted file, but the raw file. So what happens is that the signing comes first. And so in this instance, the hash is calculated, and we know that the hash is calculated, and then that hash is signed with my private key because I was asked first about the need for a passphrase to unlock the secret key. And so the signing occurs first, it's hashed, and then the hash is signed with my private key. Then it starts asking about the use of the public key. And so now we're going to encrypt with the public key of craigep@daytonastate.edu. Use this anyway, yes. And now let's take a look at the files. And there's the MD5 list.asc. Let's take a look at that. And this includes both the encryption, the encrypted file, as well as the signature. Let's get out of that. And now we need to copy that file over to the other computer so that that person can unencrypt and verify the signature. And there's our file. And now we need to decrypt and verify. And actually we need to decrypt because the verification process will automatically occur, and we'll see that happen here. So we want to decrypt md5 list.asc. So let's give us the passphrase. And there are the results. So the file was decrypted and it was verified. It's a good signature from philip@krager.met. Good signature from philip.krager@gmail.com. Again, it warns us this key is not certified with a trusted signature. There's no indication the signature belongs to the owner. Remember, if we have other people signing our keys and uploading them, that then when others use our public keys, is that there will be a greater level of trust involved with those keys. And of course there's our fingerprint, and that's our unique ID. So that ends this video on the using GPG for both symmetric encryption and asymmetric encryption, and we've showed you how to use both for encrypting and decrypting files and how to create digital signatures.